Igor Borovikov. The paper I present is titled Applied Monocular Reconstruction of Parametric Faces with Domain Engineering. My co-authors are Karine Levonyan, John Rein, Pawel Wrotek, and Nitish Victor. All of us work at Electronic Arts in Redwood City, California. We start with an introduction and motivation, then explain the face-to-parameters problem, or F2P for short. Next, we will explain how decomposition can help us with training ML models in the F2P problem. Also, we will briefly discuss the experiments we conducted. Finally, we will touch upon the subject of style transfer and mapping between models. The conclusion and future work will wrap up this presentation. The main goal of our work is generating virtual character faces from photographs using machine learning. We focus on parametric models because of their importance for creating virtual worlds. The next two slides capture at a conceptual level the main difference between fully morphable mesh for head modeling and the parametric approach. On this slide, we explore the morphable meshes. They represent one way of creating character faces in computer games. The mesh representing face allows to manipulate details of its topology all the way down to the level of vertices. That provides a lot of freedom in modeling and lots of potential for high realism. Obviously, editing fully morphable mesh would require an experienced modeler. Also, it takes quite a bit of time to achieve the required quality. When modeling is completed, we have to store the entire mesh and load it to construct the character in the target application. The amount of stored data can be substantial. Unlike morphable mesh, the parametric model allows for the head editing at a much higher level, and with proper UI, that may be more intuitive than manipulating vertices. The parameters define features, size, shape, and their location using underlying prefabricated construction elements. These elements are controlled by numerical parameters. For example, we may specify width and length of a nose as numbers that control corresponding modifiers. The resulting representation is compact and can be stored and shared very efficiently. When a virtual environment has lots of different characters, parametric models offer a strategic advantage. This slide shows in some more detail how a parametric model can define the shape of a human head, facial expression, and more. In this presentation, we focus on reconstructing neutral faces. The animation here exposes only some of the parameters defining a neutral face. Flame model shown here is a popular model in academia. Unfortunately, it is hard to build and run under Windows. Make Human, while being a hobbyist tool, offers better support across platforms. It is also open source, based on Python, and easy to build and run. Conceptually, it relies on the same kind of parameterization of human faces as Flame model. Parametric models are not new by far, they are used widely. A well-known example in the industry is the Sims franchise, which offers the Create a Sim tool. It allows to control model parameters via direct manipulation and via selection of discrete elements. There are many more parametric models for modeling human heads in the industry and in the hobbyist domain. Some of them are listed on this slide. Editing a head in a parametric model, despite all of the convenience of the parametric approach, can be tedious and time-consuming. Here is a sentiment on Reddit from a Sims player who was able to create a very impressive reproduction of her likeness in CAS. This took way more time than I would care to admit. That brings up an obvious question: can we automate parameters tuning by training a machine learning model that converts a photo into the set of parameters? That's the problem of monocular reconstruction, which we discuss in this paper. To formulate our ML approach in more concrete terms, we need to take a look at the underlying parametric space. So we may have continuous parameters that are mapped to sliders and exposed to the players via direct manipulation tool. They control things like mouth width, its location, with respect to the nose and chin, nose length, etc. There are approximately 90 parameters that we need to compute with our ML model in Make Human. Discrete parameters correspond to other type of elements. They bring in gross changes to the underlying mesh. They may also come with a texture that enhances the results visually. The total number of discrete elements in one of our applications is around 300, but they are broken by facial regions and as such are split by subspaces. Also, there are other discrete elements like color palette selections, hairstyle, accessories, etc., which we are not covering in this presentation. To formulate our machine learning problem, we need the parameters as a vector paired with the input image. For our purposes, all the training data is generated by an instrumented MakeHuman or some other target application, which can randomize a character, render it, and save the corresponding facial parameters. That makes our training dataset. We also use transfer learning, starting with a pre-trained CNN. In particular, we found that inception model gives good results. Using transfer learning speeds up training considerably. Next, we need to define loss function, which will be optimized during training. For F2P problem, the loss is the difference between the predicted and the actual values of the parameters. Just to be totally clear, we are not comparing any images during training. All loss is computed as a difference of vectors of the parameters. There is no loss in pixel space involved. Since our parameters are generated by the open source application for this paper, we have a complete knowledge of what parameters correspond to and what features of a face they describe. The loss naturally breaks into several parts as follows. The continuous parameters correspond to the regression part of the problem, and they map to modifiers. Regression on these parameters can use L1 or L2 loss. Classification part is for discrete elements. We compute classifier's loss as cross-entropy individually by the facial region. The slide shows the multipart loss that we have to minimize during training. R's here correspond to the regression part of the loss and C's to the classification part. The V's and W's are weights that we can tune or leave constant equal to 1. Their choice can significantly affect the speed of training, but is not as important for the final result. All facial parameters are grouped by the regions of the face, nose, mouth, eyes, etc., including general shape of the head. For the seams, we have 9 regions, meaning n equals 9 in the formula on this side. For our experimentation with MakeHuman, we limit that to just 4. The natural organization of loss terms by region is important. We use it as the basis for the decomposition later. Now, multipart loss corresponds to a single inception model that computes an aggregate output vector shown at the top right of this slide. Such model performs reasonably well, but there is a way to improve it using decomposition and ensembling. Breaking the multipart loss into the components by regions and training local models separately is one way of doing it. Combining the local models with the aggregate one helps to improve the accuracy even more. Such a combination is not quite a standard way of ensembling. So we need to provide some assurance that it works indeed and is designed to be efficient. Also, we need to define how we combine predictions from the models in this ensemble. After we train the aggregate and local models, we combine their predictions with weights as on this slide. That gives the final output vector of parameters that we use to recreate a face. The weights in this weighted sum can be trained by optimizing the loss of the prediction. For the modifiers, there is direct one-dimensional coordinate-wise optimization problem for W's. For the classifiers, we have to optimize the predictions to make sure that they are on the same scale before combining them. Next, we optimize classification prediction weight by facial region. The optimization in both cases is done over the entire training dataset. That completes the definition of our ensemble and also gives the exact recipe for computing the combined prediction. Is the proposed approach indeed better than the naive aggregate one? To answer the question, we consider a couple of experiments. Our first ad hoc experiment was with a proprietary application. We trained a local model using SqueezeNet to speed up training process. The image on this slide shows the inputs, left and right columns. The second column shows reconstruction with a single aggregate model. The third column shows results coming from the proposed ensembling. The numbers correspond to the FaceNet cosine distance between the neighboring pairs of the faces. FaceNet computes an embedding that characterizes the face. Comparing the embeddings, we can measure similarity between faces numerically. Smaller cosine distance is of course better. As you can see, the distance is smaller for the ensemble-based results, as expected. Similarly, we obtained quantitative results while experimenting with Make Human software. The results for CNNs trained on local features combined with the aggregate model were measurably better over a large dataset. Also, as expected, the proposed ensembling outperformed a naive combination of models. We skip the tables from this presentation. Please check the paper to see the numbers. Showing them during live talk is a little bit boring. On this slide, we show why local models give a notable improvement for the accuracy of the prediction. When we train a CNN using transfer learning, we can do it in a feature extraction mode or with fine-tuning. In the first case, with feature extraction, shown on the top row, we update only fully connected weights, denoted as FC. By observation, we can see that if we use the full images for training, then it would not make a notable difference if we trained with multipart loss or just a slice of it. That's because the weights in the FC layer are trained essentially independently from each other. Feeding cropped images into feature extraction allows to focus on a concrete facial region. That may improve results a little bit since the features are now at a different scale. But again, we do not expect a radical improvement over multipart loss computed from the full image. The reason is the same. The FC layer trains on slightly different but very similar features. In fine-tuning training mode, we updated all the weights of the CNN. In this mode, focusing only on the vector slice instead of the full multipart loss can bring in the advantage. That's because the weights tune to a smaller target. Even larger advantage provides feeding in crops corresponding to the local features. That's because the CNN now doesn't have to learn to ignore features from other regions. We observe all these effects in our experiments with Make Human software as well as with the proprietary application. Bottom line, the fine-tuning mode gives the most accurate version of the proposed ensemble. When discussing the F2P in application to the proprietary software and to Make Human, we skipped an important topic of domain shift and domain adaptation. We used training data generated by the target application itself. Obviously, the faces generated this way are only stylized representations of humans. Their faces may look cartoonish or have unrealistic lighting, etc. Yet we applied our trained with the synthetic images CNN models to the real-world images. That did not affect performance of our models considerably, but it still brings up some questions. The situation when the distribution of the training data is different from the one in the production is called a domain shift. One way to address it is the domain adaptation. For the proprietary application, we trained a style transfer model based on StyleGen2, which converts a real face into a cartoonish stylized face. Feeding the stylized images of the face instead of the original ones into the ML pipeline improved the prediction accuracy. Interestingly, it worked even better when we combined it with the decomposition approach. Unfortunately, StyleGen2 doesn't have a liberal enough license to include it into the commercially available pipeline. However, it suggests a potential direction for future development to bridge different domains in an efficient manner. With the proper style transfer, we may feed other types of images into the ML pipeline, sketches, painterly images, etc. Of course, we need a concrete style transfer model trained for each style we want to use for inference. These models would serve as an adapter and would not require retraining of the main CNN. Now let's put everything together. This slide summarizes the proposed approach. We trained several models. One is for style transfer, it converts the real-world input image to the style expected by the ensemble. Next, we run segmentation to localize features like nose, mouth, eyes. The ensemble runs specialized CNNs for local features and for the entire image. The predictions are the parameters combined with the trained weights. The target software renders the final reconstruction, which comes from the predicted parameters. In this talk, we brought up several interesting yet practical topics. Decomposition approach proves to be a useful improvement to the straightforward solution of face-to-parameters problem. Domain adaptation enhances results obtained with the decomposition approach, and also domain adaptation opens opportunities to unify creative pipelines built around different target applications and input domains. We plan to continue exploration of domain adaptation, and perhaps StyleGAN 3 will improve results even further. As a final note, we strive for reproducible research. To that end, we intend to open source our experimental code developed for Make Human. Please reach out to the authors directly or check Electronic Arts GitHub account for our paper repository. We plan to complete open sourcing process in near future. Thank you for attending.